Hey friends, welcome to Chemistry Lover, and let me start today's video by asking you this simple question that what will be the product when you treat this alpha beta unsaturated ketone with potassium cyanide in hydrogen cyanide. So if you just apply your basic concept of chemistry and you think nothing more, so you will say that the cyanide will attack on this carbonyl compound and you will get this product, right? So cyanide here, one hydrogen here, and this is your methyl group. So this is called cyanohydrine, and your answer is completely correct, but the condition is you have to do the reaction below 10 degrees centigrade. So the reaction temperature should be 5 degree to 10 degree centigrade. So if you do the reaction at 5 degree to 10 degree centigrade, your answer is completely correct. You will get this as your product. But the question is, if you do the same reaction at, for example, 80 degree centigrade, that is the refluxing condition, then what will be the product? And quite surprisingly, at this particular temperature, if you treat the compound with the same reagent, you will get completely different product, and the product is this one, right? So you can see the difference. In the first case, your cyanide adds directly to this carbonyl group, so this is a direct addition, whereas in the second case, instead of adding to the carbonyl group, it adds to this double bond, right? And this is called the conjugate addition. And you can say it in other ways, that is, if you just do the numbering for the carbon, so this is 1, this is 2, sorry, you have to number from this oxygen. So this oxygen is 1, this is 2, this is 3, and this is 4. So in first case, the addition occurs across 1 and 2, the first and the second atom across this oxygen and this carbon. So this is called 1-2 addition. So this is called direct addition or 1-2 addition. On the other hand, in the next case, it adds across this 4 position and this 1 position. So actually the product which you will get here is this. Okay, so then tautomerization of this will give you this product. So basically the reagent adds across this 4 position and this 1 position, so that's why it is called 1,4 addition or the conjugate addition, right? Now you can understand, or you get the point, that in this video I will be discussing about the 1,4 addition versus 1,2 addition, and this is the first example or very common example. So from the discussion of this particular question, you understand the fact that when you have alpha beta unsaturated carbonyl compound, now that compound may be alpha beta unsaturated ketone which is in the given question, or it may be alpha beta unsaturated aldehyde, or it may be a ester, it may be a acid chloride, it may be a amide, right? So anything. So if you have any alpha beta unsaturated carbonyl compound, you have two possibilities: either your nucleophile can add directly to the carbonyl group, or it can do the conjugate addition. And whether there will be a conjugate addition or a direct addition, that is dependent on the 3 major factors, and that factors I will discuss now one by one. Okay, so the first factor which determine whether you get a conjugate product or a direct addition product is the type of the reaction condition or the reaction condition. So the first point is the reaction condition. Now what is mean by reaction condition? So reaction condition means whether you do the reaction for a long time or for a very short interval of time, or whether you apply heat, that is, you do the reaction in a harsh condition or a milder condition. For example, the reaction which I just discussed, the addition of hydrogen cyanide across the carbonyl compound. So when you do the reaction at low temperature, you get 1,2 addition product, whereas when you do the reaction in refluxing condition, you get 1,4 product. So the reaction condition is very important. Now why is the case? Okay, So before discussing that, you should have an idea about the thermodynamically controlled product and kinetically controlled product. So when you do a reaction for a very long time, you get, or you do reaction with a harsh condition, you get the product which is more stable, and that is called a thermodynamically controlled reaction, and the product is called thermodynamically controlled product. Whereas if you do a reaction for a short time and milder reaction condition, the product which you get as a major product, it is a kinetically controlled product, because that product is formed faster. Now in some cases, the both thermodynamically controlled and kinetically controlled product may be same, but that is not our point. So let us see why this product, when your cyanide adds across this carbonyl group, is a kinetic product, whereas this is your thermodynamic product. So we have to understand why the second one is thermodynamic product, whereas this is KCP, kinetically controlled product, and this is TCP. So we have to understand this. Now how can you understand? So your starting material is this. Okay, so this is your starting material. Now before discussing the fact how it is thermodynamically controlled product and how it is kinetically controlled product, let us see how the 1,4 reaction happens at all, because you know how the 1,2 reaction happens or 1,2 addition happens. So if you have a carbonyl compound, here you have the LUMO of the carbonyl, so this is the LUMO of the carbonyl group, okay, and your nucleophile which has a HOMO with field electron that will interact with this LUMO. So this is how a nucleophile react with the carbonyl compound directly. Now what about this position, how a nucleophile adds across this position? So for that we have to imagine, or we have to draw the LUMO of this particular compound, okay, and how the LUMO of this particular compound looks like. So for that you have to compare this with 1,4-butadiene. So if you compare it with 1,4-butadiene, you can see both the structure of both compounds are basically same, only this position is occupied by a oxygen atom, right? Now what is the LUMO of this? Okay, so this, if this is your alpha beta unsaturated carbonyl compound, your LUMO will be like this. Okay, so for the first orbital, so for psi1 all the lobes will have same sign, for the psi2 there will be a lobe around this, and for psi3 there will be a lobe around this. Okay, so if there will be a lobe around this, so you can see these two will have same symmetry and these two will not have symmetry matching. So this is the structure of LUMO for the alpha beta unsaturated carbonyl compound. Now the interesting fact about this LUMO is that the LUMO has the highest coefficient at this C4 atom. So if you compare the size of this lobe and this lobe, you can see this lobe has larger size than this. So any nucleophile which has a HOMO, in terms of orbital matching, in terms of overlap, they will prefer to interact with this C4 carbon atom rather than this C2 carbon atom. So overlap will be favored in this C4 position. So that's why this 1,4 addition happens. Okay, now why the 1,2 reaction is so common? Because any negatively charged nucleophile, if you have any negatively charged nucleophile, their reactions are controlled by the charge, the Coulombic interaction, and if you put the delta positive charge, all these two carbons atom will have the most delta positive character, but you can see this center is more close to this electronegative oxygen atom, so the amount of delta plus will be much higher at this C2 position than this C4 position. So any nucleophile whose reaction is controlled by charge, that will prefer to attack on this. Okay, so this is another fact. Now if we take this with our mind. So now we can explain how the KCP and TCP is formed. Okay, so this was our compound and our cyanide, which is negatively charged nucleophile, so its general tendency will be to attack on this carbon. Okay, so if it attacks on this carbon, it will form a tetrahedral intermediate like this. Okay, so it will form a tetrahedral intermediate O minus. Here you will have cyanide and here you will have methyl. Now this tetrahedral intermediate, after protonation on this oxygen, it can give this KCP, the kinetically controlled product, or it can also collapse back to give you the starting material, right? So this reaction is in equilibrium. This KCP, kinetically controlled product, and this starting material, they are in equilibrium. That is, this tetrahedral intermediate can either go to this direction or it can go to this direction. So this is in equilibrium. So every time one molecule is formed, there is a chance that it can revert back to the starting material also. Now on the starting material, although the chance of 1,4 addition is very less, but for 100 molecules there will be at least 20 or 10 molecules will be there which will undergo 1,4 addition. So if 1,4 addition occurs, what you will get? So you will get this. Okay, so O minus, this, here you have cyanide, and now you have HCN. So then this will be protonated to give you this thermodynamically controlled product. Now you can see this reaction is a irreversible reaction, and at the moment when any 1,4 addition product forms, there is no coming back. So if this product is formed, it cannot come back to the starting material. Okay, so this is an irreversible reaction. So if you allow a longer reaction time, or if you give heat to the reaction, do the refluxing reaction, then what will happen? Your kinetically controlled product, which formed faster but also revert back to the starting material, that will undergo the 1,4 addition, and it will give a product which is not reversible or which is stable, and that's how allowing more reaction time will give you the 1,4 addition product or thermodynamically controlled product. So you understand how this thermodynamically controlled product forms. Now the point is why we say that this kinetically controlled product is less stable, whereas this thermodynamically controlled product is more stable. So for that you have to look into the bond energy, right? So if you see that which bonds are broken and which bonds are formed, the point will be clear. So in the starting material you have one carbon oxygen double bond, one carbon carbon double bond, and in the KCP, the kinetically controlled product, your carbon oxygen double bond is broken, whereas your carbon carbon double bond is intact. And by breaking this carbon oxygen double bond, you form a carbon carbon single bond and oxygen hydrogen single bond, right? Now this carbon carbon single bond it has a much lower energy. The carbon carbon single bond has much lower energy than carbon oxygen double bond. So that's why with respect to energy, this product is not very much stable. Whereas in the thermodynamically controlled product, you can see you destroy the carbon carbon double bond, whereas the carbon oxygen double bond, which is stronger, it is intact. You destroy only the carbon carbon single bond, and instead you form a carbon carbon single bond and carbon hydrogen single bond. So their total bond energy, the carbon hydrogen single bond and carbon carbon single bond, will have much higher energy than a carbon carbon double bond, and that's why with respect to energy, this particular compound is much more stable, and that's why it is thermodynamically controlled product. So by this particular example, it is clear that how the reaction condition controls whether a reaction will be thermodynamic, whether a reaction will give you 1,4 addition product or 1,2 addition product, right? Now let us discuss about the second important point, that is the type of the nucleophile. Okay, so type of the nucleophile, what type of nucleophile you are using, that is very important factor. So our next point is the type of nucleophile. Now again, for that you have to look at the structure of the alpha beta unsaturated carbonyl compound, and you can see for this alpha beta unsaturated carbonyl compound, this is one electrophilic center, whereas this is another electrophilic center, and their nature is totally different. This electrophilic center, it has high delta plus charge, so it is highly positively charged because of the presence of this electronegative oxygen atom, right? So it is a hard center. So this electrophilic center, this 2 position, is a hard electrophilic center, whereas this position, it merely contain any charge. Most of its reaction is controlled by its orbital interaction, and that's why it is a soft center. Okay, so this center is a soft center, whereas this center is a hard center. Now if you add any hard nucleophile, that will prefer to attack on this carbonyl carbon atom directly, whereas if you add any soft nucleophile, that will prefer to attack on this 4 position. For example, if you do the reaction of this alpha beta unsaturated ketone with this thiol, you don't need any acid or base catalysts. It will attack on this 4 position to give you this product. So you can see, if you add this alpha beta, if you add this thiol, it will always attack on this 4 position, because this sulfur based nucleophile, they are very soft, right? Whereas if you do the reaction with a hard nucleophile, for example, if you do the same reaction with so you may do the reaction with, so we already shown the example of cyanide. So cyanide is a charged nucleophile, and we can consider it harder with respect to this thiol. So we have seen that depending on the reaction condition, it can add on this carbonyl group, right? So this is the case. So hard if you add alkoxide, so depending on the reaction condition, the alkoxide RO minus, that can add either on this 4 position or on this 2 position, but mostly it will prefer to react on this 2 position because it is a hard nucleophile. Now if you compare nitrogen based nucleophile, for example amine, if you add a secondary amine, for example R2NH, if you add a secondary amine, compared to oxygen, nitrogen is less electronegative, and that's why we can consider it as a softer nucleophile than oxygen, and that's why it will prefer to attack on this 4 position, and you will get this. Okay, so you will get this product. So when you compare, you have to compare the reactivity. You have to always look into the nucleophile, whether it is soft or hard, and these are some examples, but the most important example of this soft and hard nucleophile is when you consider the reaction of alpha beta unsaturated carbonyl compounds with Grignard reagent. So if you have a alpha beta unsaturated carbonyl compound, and if you react it with Grignard reagent, that is RMgBr, what will be the product? So the major product will be the addition across this carbonyl group, and that will give you this alcohol, right? But if you do the same reaction with RMgBr and add a 1 mole% of copper plus, that is CuCl, copper 1, right? Copper 1 ion. So what will be the product? In this case, you will get the 1,4 addition product. Okay, so this is a drastically different result. Now why so? So we can say that for RMgBr, for the Grignard reagent, this magnesium 2 plus, it is a hard center, and due to the symbiotic effect, this R minus also becomes harder when it binds to magnesium, whereas when you add copper, there will be a compound like this. So the exact structure is not known, but you will get something like this, R2Cu minus, and there will be some positively charged species to make up this negative charge. So basically your R is now bound with this copper. Now copper 1 is a soft species, because if you compare the electronegativity of magnesium and copper is more electronegative, so that means it will be a softer species, and again due to symbiotic effect this R minus becomes soft, and now it will prefer to attack on this 4 position to give you this product. So this is a very famous example. Now so you can see that the nature of the nucleophile also decide whether a reaction will give you 1,2 addition product or 1,4 addition product. And now let us discuss about the third point, that is the type of the alpha beta unsaturated compound or the type of the electrophile. So type of alpha beta unsaturated carbonyl compound. So this is again a very important. Now for example, if you have alpha beta unsaturated ketone, and if you have alpha beta unsaturated ester, right, or if you have alpha beta unsaturated aldehyde and alpha beta unsaturated ester, so what will be the reaction? So if you add sodium borohydride, in case of alpha beta unsaturated aldehyde, your sodium borohydride will attack on this alpha beta carbonyl compound directly to give you this product. So this carbonyl group is only reduced, whereas in case of alpha beta unsaturated ester, it will reduce the double bond and your ester group remain intact. Okay, and so you can see, so whether your so you use the same nucleophile sodium borohydride, but the reaction outcome is dependent on the type of the alpha beta unsaturated carbonyl compound. So in the first case, this alpha beta unsaturated center, this particular center is very much reactive because it is a aldehyde. In terms of steric hindrance, in terms of electronic factor, it is very much reactive, very much electrophilic. But in case of ester, you can see this oxygen has a plus R effect, and that reduces the electrophilicity of this center. So instead of adding to this 2 position, this nucleophile will prefer to attack on this 4 position, and you will get this. And now this product will not be reduced further because sodium borohydride cannot reduce ester. But if you use some ketone, for example, if you use some ketone, so in case of ketone also, this carbonyl group is not that much electrophilic, so your sodium borohydride will have higher tendency to attack on this 4 position, and you will end up getting this first, and which will be further reduced to give you this alcohol, right? So this is the case. So you can see how this the type of the electrophile or the type of the alpha beta unsaturated carbonyl compound determine whether a reaction will be 1,4 addition or 1,2 addition. And for in case of ketone, you can get exclusive 1,2 addition product with sodium borohydride also, but for that you have to use this cerium chloride. So if you do the reaction of ketone with sodium borohydride in presence of cerium chloride, so then it will undergo the 1,2 addition, that is your hydride will add across this C2 carbon atom. So because in this case this oxygen is coordinated with cerium chloride, and now you can see this positive charge will be there. So now this particular position will be very much activated, and your nucleophile will attack here. So although this is not the sole reason, this is a fake explanation. If you want to know the real reason of the action of cerium chloride, I have a separate video on that, you can watch that. Okay, so the point is, the nature of the alpha beta unsaturated carbonyl compound determines whether the reaction will be 1,4 addition or 1,2 addition. Similarly, if you consider between the acid chloride, so if you have acid chloride, which is alpha beta unsaturated carbonyl compound, and an amide, So you can easily say that this amide, this carbonyl group is very much is not very much electron deficient. Its electron deficiency is reduced by this plus R effect, so it will prefer to undergo 1,4 addition, whereas in this case, due to the presence of this chlorine, which shows minus I effect, and that makes this center more electron deficient, and that's why it will undergo the 1,2 addition. So the type of the electrophile or the type of the alpha beta unsaturated carbonyl compound is also important. So the overall conclusion is that whether a particular reaction will give you 1,4 addition product and 1,2 addition product, that you cannot decide by just looking at the reaction. You have to take care about several factors, that is the type of the nucleophile, the type of the alpha beta unsaturated carbonyl compound, and also the reaction condition. And if you look at all these topics, and if you solve problems from this particular topic, I am sure that you will be able to get the point, and you will not have any problem in solving the questions in the exam. So hope this video will help you, and thank you for watching. If you are new in this channel, then subscribe my channel.